So if you want me to give you a science-y definition, radioactivity is the release of energy or particles as the result of the, well, you might be able to figure out where all the action is happening for radioactivity because we call it a nuclear reaction or a nuclear bomb or a nuclear reactor. Which part of the atom do you think?
Nuclear.
The nucleus.
Nuclear.
The nucleus. So unlike the last unit, Kalish, where everything was happening in the valence electrons, here we're looking at the center of the atom. Only some forms of some elements are radioactive. So not every element is radioactive. Some are stable.
Noble gases.
But some of the non-noble gases are also radioactively stable. But a lot of them you've heard about. So Oren already mentioned uranium, but also some further up on the periodic table. So radium, I think you were mentioning the radium girls. That was the first radioactive element that was isolated by Marie Curie. She won a Nobel Prize for it, but it also ended up eventually killing her. Potassium is radioactive. Every time you're eating a banana, believe it or not, you are getting some radioactivity. She won two. She won one for physics and one for chemistry. And her daughter also won a Nobel Prize. So it's a very successful family. First of all, there's something called background radiation. Background radiation is everywhere. And it's harmless. In other words, if I took a Geiger counter, which measures radiation, and I brought it to this room, and I turned it on, it would click. There's always radiation throughout the whole universe. It's called the cosmic background microwave radiation. We use a Geiger-Mueller counter or a Geiger counter to measure radiation directly. Yep.
Can you zoom in a little bit?
Not with keeping the whole sentence on. Maybe a tiny bit.
Yeah, that's what I'm just trying to do.
About like that, maybe.
Yeah, that's good enough.
I got to go down a little bit. There.
Thanks.
So this first bit we already know. It says draw a diagram of an atom. Quiet, please. Include the 3 subatomic particles. So here's our nucleus. What's inside the nucleus? So this time, let's draw some protons. Let's draw some circles and put little P's on them for protons. And let's draw some more circles and put little N's on them for neutrons. Let me make this a little larger so you can see. So I'm imagining the nucleus has some protons and some neutrons in it as well. And they're packed inside. And then we have outside here the electrons. And the key idea you can write next to this is the nucleus contains which 2 particles? P plus, I'll get back to the middle of the screen in a second, and N0. And these can change. We didn't know that until the beginning of the last century, around the 1900s, but these can change. There are 2 main types of radiation, and the first is energy, pure energy. This is the one that does the damage. When you see movies and they show people being exposed to radiation and getting all blisters on their skin or getting all sick, this is the type of radiation they're talking about, and it is gamma waves. You may have noticed, Ariel, that I like to abbreviate, and so there is an abbreviation or a symbol for gamma. It's sort of like a fish standing on its head. That's the symbol for gamma. If you want to use that symbol, I'll absolutely know what you're talking about. If you look at your green sheet where it says gamma rays underneath radioactivity symbols, You can see that's the type font version. It's sort of supposed to look like that, but all of us just kind of do a fish doing a headstand. We know what you mean. Where have you heard of gamma rays before in the movies? Yep. Okay.
Oh, you okay.
The Hulk is not actually real, clearly. If you got exposed to gamma rays, it would not be good.
What do you mean I turned into a horse?
I know.
You just want to continue from getting my full power.
So gamma rays are part of what we call the electromagnetic, good, you remember that word from grade 8, spectrum. They're a type of light, a very, very high energy light. In fact, someone earlier here, when I asked what's radiation, what are some good uses, they said X-rays. X-rays, you don't want to do too many of them, but one X-ray is not going to harm you. But you can see gamma rays are even more energetic than X-rays. You would not want to get exposed to gamma rays.
Oh, don't worry, the X-rays. I can get like a bunch.
Sorry, hang on. Question, Casey?
I was gonna say, maybe that's why when you go get an X-ray, you have something.
Oh, yeah. They'll always, or if you're getting a dental X-ray, they'll make you wear a lead vest lined with lead because they only want to expose as little as possible of you to X-rays. Multiple X-rays can also eventually perhaps do some damage, but if you're getting like 2 X-rays a year, don't lose any sleep over it.
Wait, I have a question.
I have an answer.
When I was little, I had nipples and I had to get a bunch of X-rays.
When you're small, probably you're still okay because your body is still able to repair and fix things very, very good.
Okay,
Kids heal far better than grown-ups.
Is that MRI the same as that?
So Kalish asked a great question. He said, is an MRI the same as an X-ray? No, an MRI is actually using magnetic fields, but for what it's worth, it used to be called a nuclear MRI because it's actually, there's some nuclear physics involved. People wouldn't go in it because people are scared of the word nuclear. So they dropped the N and called it MRI, which stands for magnetic resonance imager. And people go, oh, magnets, I have those on my fridge. I'm fine with getting into that machine, even though the nuclear is still there. Hashtag nerd trivia.
What if I ate a bunch of pennies before I got one?
Remind me later on, I'll show you some, I have a couple of videos on MRI machines.
I've
Yep.
heard some MRIs before.
Remind me later and I'll show you a good video. Okay? Yeah. That's positrons, which is a different, that's a quantum physicsy thing. The P for PET stands for positrons, which are essentially positive electrons that we can artificially create.
Really? But that's more dangerous? Or
No.
dangerous?
Wait, I have another question.
Yep.
How is radiation used like for cancer?
We're going to get there. So, the first type of radiation is energy. Gamma rays. Bad. Shh. In the back row there? Thank you. There's another type, particles, and the two main ones are alpha particles, and the abbrev for that is a fish on its side. That's actually where our lowercase letter a comes from. You can kind of see it hidden in there. And if one is alpha, can you guess what the other one might be called? Beta particles. And the abbrev for that is a capital B with a tail, and yes, that's where our capital letter B comes from. Ariel, can you get off your phone, please, before I lovingly take it away? Thank you. I could politely ask you to give it to me, or you can just put it away. Or you can just
could destroy
okay.
it.
So, alpha symbol, beta symbol, and these are emitted by the decay of some atoms. Again, if you forget the symbols, they're all on your green sheet. So what was that?
I said, what kind of symbol is that?
That's the Greek letter alpha, that's the Greek letter beta. That's where our A and B come from, and you can also see that's where the word alphabet comes from. It literally means A, B's.
That does not look like an
Lowercase
A.
a?
P and a P.
Lowercase a? Absolutely looks like a lowercase a.
Oh, no.
It's a little more.
Just get rid of that part.
Yeah, erase that part and see
Yep, that's where it comes from.
it looks like fish.
Next page over. So we're going to talk about radioisotopes, or just isotopes for short, because we tend to abbrev. Different atoms of the same element can have different numbers of neutrons. And this we haven't talked about much. When you were finding how many neutrons on the test you just wrote, you were really finding the most common number of neutrons, but it can change in some atoms. So if you change the number of neutrons, you get different masses. The mass on your periodic table is actually just a proportional average. It's the average mass of all of the isotopes. Okay? And here is the key sentence coming up right now, so you want to zone in. If you have an atom with the same number of protons, but it has a different number of neutrons than its buddies, that's what we call an isotope. So an isotope has an unusual number of neutrons, and often that makes it unstable. The nucleus is just too crowded, or not crowded enough, and it's not a stable nucleus. Sorry? Yep, I think Ms. Buck and Ms. D'Onofrio might have done something. Yeah? Quick like a bunny. Actually, can you wait for about 5 minutes and then, because this is the key part here. So here is our standard atomic notation. We have a number here, and a symbol here. Where the big X is, that's going to be the element symbol. Quiet, please, in the back corner. Thank you. A is going to be the mass, and Z is going to be the atomic number, which is also the number of protons. We call this the nuclear symbol. So here's an example, okay? And I put this, I think, on your green sheet, so you don't need to memorize it. You probably will, because you'll get sick of looking it up, and that's really the only reason you should memorize something, is because you get sick of looking it up. But it's on your green sheet right on the very, very top where it says notation, A, Z, X. X is the symbol,
The gamma.
K, potassium. A is the atomic mass, and Z is the atomic number. So there are many types of uranium, for example. We would call this first one uranium-235. We would call this next one uranium-238. How many protons does uranium have? 92 no matter what, so that number doesn't change. But what's the mass of uranium-235? Well, let's fill this in. First of all, where the letter A is, that's the symbol, uranium, for both of them. Where the letter Z is, that's the number there. So they both have a 92 and a 92 because that's the number of protons. What's different? The mass. Sorry, you know what? Cassandra, you're right. Mr. Dewick totally botched that. The A, I put the mass, didn't I? So that should be a 235. That's totally my fault. And a 238. Candy for you because you caught me making a mistake. The U is the symbol, uranium. Yep. So here's the key. If you, on your calculator, can you go 235 minus 92 for uranium-235? How many neutrons does it have? How many? It's got 143 neutrons. Uranium-238 has 3 more. How do I know it has 3 more? Because I got an extra mass of 3. And if I go 238 minus 92, I get 146.
Wait, what is the 146?
If you go 235 on your calculator minus 92. Right? So we're finding the number of neutrons the same way we did before by going mass minus protons. The only change is I have to tell you the mass because it might not be the one from the periodic table because I may be giving you an isotope. So this is a pretty good notation. These are radioactive and they decay into different elements. So let's look at potassium. Turn the page. There are three main types of potassium. Ariel is potassium 39, potassium 40, and potassium 41. Okay? Find potassium on your periodic table. I'll even tell you it's element number 19, and it's K. So everybody right now put a big K right there, a big K right there, a big K right there. What's the mass of potassium 39? 39. So I would put a 39 right there. What's the mass of potassium 40? I would put a 40 right there. What's the mass of potassium 41?
41.
Now, if you look on your periodic table, the mass given for potassium is 39.1. These two are non-stable isotopes. Now, the number that's going to go right here is the number of protons, the atomic number. What's the atomic number of potassium?
19.
So then, here's the question. How many neutrons does potassium 39 have? You can go 39, take away 19. How many neutrons does potassium 39 have? 20.
I put 30.
How many neutrons does potassium 40 have?
30.
Nope. How many neutrons does potassium 40 have? 40 take away 19, which is? And you can also figure it out by saying, you know what? Its mass got one bigger. It must have an extra neutron because it can't gain a proton. How many? Yep.
I thought this was science, not math.
There's going to be some math in this. That's why I said you need a calculator. How many electrons? Well, 19, 19, 19. So if you want the potassium breakdown of a typical banana,
Go back up, sorry, I forgot this.
19 electrons, 19 and 19, because that's the same number of protons, because these are neutral atoms. These aren't ions, they're radioactive. What's going on is changes with the nucleus, not with the electrons. So a typical banana, every time you eat a banana, almost all of it is the stable potassium. There's about 6.7% that's potassium 41, which is radioactive, and then 0.01%, which is potassium 40, which is also radioactive. But your body deals with that just fine. This is not saying don't stop eating bananas. Put your pencils down, look up. So I used the term decay. I said to you, the reason he could go near Chernobyl is the radiation has decayed, and now basically you could live there and probably be fine. Maybe not, but probably. Okay? Certainly not the hospital where the fireman's clothing is, but Chernobyl itself, since they removed the topsoil, it's not too bad. So isotopes decay. Radioactive decay is the process in which unstable nuclei, which is the plural of nucleus, lose energy. How do they lose energy? By emitting energy or particles. By emitting gamma rays or beta particles or alpha particles. Atoms are only radioactive if their nucleus is unstable. And I'm not going to explain to you what makes a nucleus unstable. It's a quantum physics thing and it's complicated, but some nuclei are stable, some nuclei are unstable. We cannot predict if a certain atom will decay, but if you give me 1 trillion atoms, I can tell you on average what percentage will decay. So we have no technology. In fact, we think it's impossible to predict that that specific atom is going to decay. But if you give me a big sample, I can say, give me an hour and 30% will have decayed. Isotopes are unstable. and isotopes that are unstable and therefore able to decay are called radioactive or radioisotopes. When unstable atoms emit particles or energy, we say they have undergone radioactive decay. And I'm just going to finish with this table or chart, and then Ariel, you can. But let's walk through this. So fill in the blanks. And then, did I give you this chart in your notes? I did. Okay? On your green sheet.
The gamma sheet.
Yes, on the front of the green sheet, can you please find where it says common isotope pairs? And can you find uranium-238? And then can you tell me its half-life in billions of years? What that means, it takes 4.5 billion years for half of it to decay, and another 4.5 billion years for the remaining half to decay, and another 4.5 billion years for the remaining half to decay. We call this a half-life decay graph, and I'll show you how those work in the next lesson. But it goes through 14 different decay steps before it eventually becomes lead-206. So uranium, if you look at the little chart here, first of all, it decays into thorium. It does that by getting rid of 2 protons as an alpha particle. Then a nucleus splits and it turns into palladium. Then it turns into another uranium, but this time 234. Then it decays into thorium. Then it decays into radium-226. Then it decays into Rn-222. Then it decays, I got to keep going for a reason, have patience. Decays into polonium. Then it becomes lead, but not a stable type of lead. Goes into bismuth, polonium, another type of lead, but not a stable type of lead. Bismuth, polonium, and ends up here. Now, why is this so important? If you give us a sample of uranium, we can look at how much of each of these are in it, and I can tell you how old it is. This is how we do radioactive dating. It's more complicated than that, but basically, if you tell me how much of radium and rubidium and polonium and thorium there is, I can tell you approximately how many years, how many hundreds of millions of years have gone by, and I can be pretty accurate. So one use for this, for radioactivity, is radioactive dating. Okay? So we're going to pause here